Hello, and welcome to Big Day in Education. I'm Ryan Baker. Today we continue with our second video of week 3 of the course, discussing data synchronization and grain sizes. So you have ground truth training labels. How do you connect them to your log files? This is the problem of synchronization. It turns out to be intertwined with the question of what grain size you're going to use. With grain sizes, the question is, what level do you want to detect the construct at? So let's take an orienting example, which we'll use for today's lecture. Let's say you want to detect whether a student is gaming a system, and you have field observations of gaming. Each observation has an entry time, in other words, when the coder noted the observation, but no start of observation time. So we don't know exactly when they started observing, we just know when they stopped. The problem is similar, by the way, even if you have a time for the start of each observation, because you don't really know if you can trust those start times. Do people really start when they say they start, or do they really start a couple seconds after? And for that matter, do people really stop when they say they stopped, or do they actually stop a couple seconds before? So let's say your data look like this. In the span of a week, from Monday 8 a.m. to Friday 3 p.m., we have a certain time that the student's working in the system. And at certain moments during that time, we have gaming or not gaming observations. When the observer notes the student's gaming, we make it red, and when the observer notes the student's not gaming, we make it green. Now you notice the gap between observations. Maybe the students were off this day. Maybe they didn't use the learning system this day. Or maybe the observer couldn't make it. We don't really know, and at some level, it doesn't really matter. So what grain size do you want to detect gaming at? You could detect it at the student level, the day level, the lesson level, the problem level, the observation level, the action level, or other levels, and we'll talk about each of these. The student level. To get the student level, you average across all of your observations of the student to get the percentage of observations that involve gaming a system. So for example, if the student has 5 gaming observations across the whole span of time and 10 non-gaming observations, we say that on the average, the student was gaming a system about a third of the time. Now this is not a perfect assessment. It's a bronze standard. The true number is maybe 30% or 48%. This 33% involves just a sample of the times, and you can't really get around that. But still, the center point of that sample is better than not knowing anything at all. So we just say across the whole span of time, the student was gaming a third of the time. Now this approach was seen pretty commonly in early behavior detection work when synchronization was difficult. These days we have Android apps that can do synchronization between field observations and log files, and we have coding systems for video coding that can do the synchronization. But back in the good old days, a decade ago, when we did it on like paper clipboards, synchronization was hard, even if you had a stopwatch. Now this actually makes sense sometimes even now. For example, when you want to know how much students engage in a behavior overall. To, for example, drive overall reporting to teachers or administrators. To tell the teacher, this kid was gaming more than this other kid. And to drive very course level interventions. For example, if you want to select 6 students to receive additional tutoring over the next month, you may just want to get the 6 students who game the system the most or who learn the least. A second level you can do this at is the day level, where you average across all your observations of the student, but only on a specific day, to get the percent of observations that were gaming on that day. So for example, we might say Monday is 40%, Tuesday, well, 0%, but we actually don't know if that even means anything at all because really Tuesday is missing. Wednesday, 20%, Thursday, again, 0% or missing, and Friday, 40%. Now this affords finer intervention than the student level, but it's still better for course level interactions because when you think about it, you're only going to be intervening at the most at the end of the day, probably. A third level you can aggregate at is a lesson level, where you average across all your observations of the student within a specific lesson to get the percent of observations that were gaming. In this case, we might say lesson 1 is, you see the black line in the middle, lesson 1 is 40% of the time, and lesson 2 is 30% of the time. This can be used for end-of-lesson interventions, and it can be used for evaluating lesson quality, both of which are common things that people might want to do. At the problem level, you would average across all of your observations of the student within a specific problem. We're kind of getting narrower and narrower to get the percent of observations that we're gaming. So for example, if you say the black line split problems, you might say, okay, we had a bunch of problems during this time. You can actually see that there's nothing going on in the middle, so the student probably wasn't using the system at all. And this can be used for end-of-problem or between-problem interventions, which are a fairly common type of intervention. They can also be used for evaluating problem quality, which problems are more disengaging than others. The challenge is that sometimes observations cut across problems. This is less common and easier to deal with lessons because, in particular, lessons often have a little pause between the lessons, which means you don't get as much of the cross-cutting observation. But you definitely get observations where the student was doing 2 different problems during the observation. When this happens, you can assign the observation to the problem when the observation was entered, or the problem which had the majority of the observation time, as far as you can guess, or both problems. Another level you can do these at is the observation level, where you take each observation and you try to predict it individually. So for example, we have each of these observations. Each one of these red or green lines is now something we're going to try to predict by itself. This is the most natural mapping because you're trying to predict the data at the exact level the data was collected. And it affords close to immediate intervention. If you have 20-second field observations, you can do your interventions every 20 seconds. It also supports fine-grained discovery of the model's analyses, like we'll talk about more the last week of the class. The challenge is synchronizing observations of log files, which is a harder challenge for this kind of grain size than for the other ones. In particular, you need to determine which time window each observation occurred in. And usually you only have an end time for the field observations, and you have to guess a start time. And even if you have a start time, exactly where in the window did the desired behavior occur? And how much do you trust your synchronization between observations and logs? Our Android app gets within 1 or 2 seconds, and actually both the app and the software connect to the same internet time server. What causes the 1 or 2 second delay can often be network latency. So you're never going to get perfect synchronization in this day and age. If you don't trust your synchronization very much, you may want to use a wider window. Even if your observations were officially 20 seconds long, you may want to look at windows of 30 or even 40 seconds. And how do you transform from action level logs to time window level clips? That's actually a challenge for this kind of approach as well. It's also a challenge for some of the coarser approaches. You can conduct careful feature engineering to create meaningful features out of all the actions in a clip. This is a time-consuming approach that's probably the best approach. Or you can take all the actions in a clip and take their features and just hack out counts, averages, standard deviations, minimums, and maximums. And this is the approach my group uses a lot. It seems to do almost as well, and it's a lot less work. You could also apply your observation labels to each action in the time window. And then fit a model at the level of actions. So each action, each thing the student does in the learning system becomes a data point in its own right. And you take the clips and you may assign one clip to 6 different actions because 6 actions occurred during the observation. This treats actions from the same clip as independent from one another. This offers the potential for truly immediate intervention. Now some models identify the overall construct at the action level, but they validate at the clip level. This is less certain action by action, but it allows more rapid and targeted intervention in cases where we can only get a label that's a little coarser. So bottom line, there are several grain sizes you can build models at, and we've only talked about a few today. There are actually a lot of other examples. Which grain size you use determines how much work you have to put in. Coarser grain sizes are less work to set up. But also when you can use your models. More immediate use requires finer grain sizes. So there's kind of a trade-off between how easy it is to do it and how usable your detectors are. It also influences how good your models are, although not in a perfectly deterministic way. So in our next lecture, we're going to discuss feature engineering. So thanks for coming. This is Big Data Education. I'm Ryan Baker. See you next time.